Principal Researcher at Microsoft Research in Redmond.
Great. Thank you very much. And I'm quite used to hearing the band. My son played the clarinet and the tuba in the marching band. This is what I'm missing at home this week. This is a new addition to my family. Probably the good way to start the talk is with a cute little creature. That's called a samoyed, for those of you who don't know. I just wanted to, before I start the technical talk, I wanted to introduce myself and the group I'm in. So in Microsoft Research in Redmond, we have a group called Research in Software Engineering. And I co-manage that with Wolfram Schulte. We have a bunch of our technology is available at the URL riseforfun.com. We do a lot in software tools, so you can play with some of the tools there. And if you want to know more about our research papers and such, you can go to research.microsoft.com/rise. And there are the 34, 35 actually, some odd people who make up research in software engineering. So that's a department's worth of researchers in software engineering. It's about 10% of Microsoft Research in Redmond. So we have quite a big initiative in many areas. If you think about our group, we divide into essentially working groups along the lines of formal methods. So this ranges everything from high-level design to theorem proving, logic, programming languages. We do programming language design, type theory, program analysis. We have a wide range of interests, from abstract interpretation to test generation to code contracts. We do quite a bit in also compilation technology and performance via runtimes, and also empirical software engineering. So what I did to just give you an idea of where those 35 people land, we have these working groups and people subscribe to each of them. So here I made a little social network. So here we have the working groups, and we have the people in research in software engineering and their subscriptions to the working groups. So you see empirical software engineering, so it's actually our newest group. Nachi Nagapan, Chris, Tom Zimmerman are in that. We have a lot of people. We're very heavy over on the compiling, programming language, program analysis side. That's historically where we started, with compilers and program analysis for defect detection and verification. So we have a lot of people working on that area. We have folks like Shivendu, Ken McMillan Margus, who work between the interface of program analysis and formal methods. These are folks generally working on symbolic methods in their application to programs, and then a whole bunch of people who focus more on the formal methods side, and then sort of in the middle, myself and Wolfram and Shaz, sort of who proclaim to be jack of all trades, master of none, I guess. But anyway, that's just to give you an idea at a very high level about who we are, and a little bit about our areas of expertise, not so much about what we do, but if students are interested in talking with me, I'm definitely available. I think I have an appointment time tomorrow, and I'm willing to cover any topic area that in research and software engineering, or anything else you'd like to know about Microsoft Research. Happy to talk with you. Okay, so that's the introduction to Microsoft Research and the group. Today I want to present to you some work that we just presented at UPSLA down in Portland, just 3 hours south of Seattle. This is joint work with Sebastian Burkhardt and Dan Leijzen in the Research and Software Engineering group, and Caitlin Sadowski and Jaehan Yi, who are students at UCSC and were interns with Microsoft Research 2 summers ago. So it took us a little while to get the publication out, but we're glad we did. It was one of, I think, 3 or 4 distinguished papers at UPSLA. And it's mainly the work of Sebastian, Dan, Caitlin, and Jaehan. And I was happy to be along for the ride and contribute around the edges. So the motivation for this work is summarized in this one slide, where we have an abstraction of a program here on the upper left. It's an infinite loop where we do some computation, and then we mutate some state and we compute again. And our claim is that this pattern of compute and mutate is actually widely found in many applications, where the compute phase is deterministic, generally is CPU bound, no I/O, and potentially parallelizable. The mutate phase, on the other hand, is non-deterministic, because during mutation you're interacting with the environment, receiving network packets, user input, and doing I/O. And this loop reflects long-running applications, something like a browser, perhaps an operating system. And in this common pattern, our goal would be to perform this loop with higher performance. That is a faster compute and mutate phase, and potentially in modern architectures with less power. So here's a list of maybe some examples. You can probably think of others. In a browser, we can think of the compute phase as, for example, doing the layout. Given an HTML document with its CSS, we need to lay out that document to be rendered. And a mutate phase might be changes to the document object model that are triggered either by JavaScript running or some user event. If we think of something like 3D rendering, we might view the rendering of the 3D image as the compute phase, and then changes to the objects in the scene being rendered as our mutate phase. Another example from graphics, I have a morphing of two images I want to do. That morph is intensively memory and computationally intensive, but if I make small changes to the picture, I might want to redo the morph and make that very fast. And the list goes on and on. So compilers, everything where I have some computation I'm repeatedly doing, I do a compile, edit, debug cycle, I make small changes to the program, I'd like to recompile, I'd like that to be very fast as well. So many sort of applications. Now what are the ways we can think about speeding up this compute mutate cycle? So one way is known as incremental computation. So the idea is, suppose I'm thinking of this compute phase. It takes some input, and it's deterministic and produces some output. Okay. Suppose then the user comes along and just tweaks the input a little bit. Okay, so maybe if we're thinking of a sorting algorithm, the input is an unsorted list, and I make a change to just a few elements of, say, a list of hundreds of thousands of elements, and the output is a sorted list. Well, I'd like, in incremental computation, if little changes to the input result in little changes to the output, then I'd like to reuse most of the computation I did in the previous phase. In this batch phase, I'd like to reuse as much of that computation, as much of its intermediate results as possible, so that the cost of doing my recomputation is proportional to this red section. It's proportional to the changed behavior. So that might be one way that I can make my compute phase faster. Another possible way is to parallelize. Okay, so in this case, I have my input and it's structured in such a way that I can compute the output by identifying perhaps independent partitions of the input and then essentially doing the same computation on these independent partitions. So maybe I have 3 partitions, and partition 1 will be processed by this processor and so on. And so now I can effectively increase the throughput for a very large piece of data if I can effectively parallelize it. And so these are 2 classic ways to think about speeding up computation, besides the usual things we would do for just speeding up pure sequential computation, like making better use of the cache or optimizing our algorithms by replacing them with ones with faster amortized complexity. So which one would you choose? I mean, if you had this expensive compute phase, what would you do? And do we actually have to choose? That is, if you chose to do one, would it be easier to do the other? Maybe you can have them both. So let's take a look at an example of how we might think about both. And that's really the topic of this talk. And really the idea is, if you've done work to parallelize your computation. What have you done, essentially? What you've done is you've identified potentially some partitioning of the input, and more importantly, a partitioning of work, and you've also identified the dependencies between the units of work. So for example, these 2 units of work here at the first level need to be completed before this 3rd unit is completed. So essentially when you parallelize and create a parallel program, fundamentally you can think of that as some notion of a task graph where independent tasks execute in parallel and then tasks are dependent on each other execute sequentially. The idea then is if somehow I could cache the results of these tasks and then determine that if an input is changed, only certain tasks need to be rerun, then I'm essentially leveraging the work I did for the parallelization, for the parallel decomposition, in order to gain incremental. So in this particular case, the change to the input requires that I recompute this upper right task, which flows to these other 2 tasks. But what's important is that this other part is unaffected by the change. And so those tasks represent potentials for reuse. And there's a piece of work that's a body of work started around 10 years ago by Umar Takar, who's now at MPI, called self-adjusting computation. And then this is the idea of dynamically tracking the dependencies between different pieces of code so that when the inputs change, you can figure out what you have to re-execute. And that work was done in a sequential setting. So what we're proposing here is that if you've done your work decomposition, for example, for multi-core, you can reuse that task-based diagram in some sense to do incremental computation. Okay, so let me make that a little bit more clear with a demo. And in this demo, what we did was we took an application written in .NET using the new parallel programming primitives. So this is a demo application. We didn't write it. And the idea is it morphs a beginning figure on the left there to an end figure on the right. And the input to the morph are the 2 images plus these morph lines, which have been drawn by the user to identify corresponding features. So everybody's sort of familiar with a morph. How would you code it? It's sort of an interpolation. What I'm going to tell the application to do is process this morph in parallel. Unfortunately, I don't have a very fast computer here, but it does have, it has 2 cores, although it shows it as 4 because of hyperthreading, but effectively when you measure it, it's about 2. So you can see all the units are busy. It's starting to morph this lady into the guy on the right. I don't know if you can see it yet. So how does this morph work? It's basically a tile-based algorithm. Each tile in the output image is a function of the 2 input images, the beginning and the end. And over time, the value of a pixel is an interpolation and a blending of pixels from the input images. Okay, so like I said, it's really slow. Even though it's parallelized. But you can see that the process is on its way. Okay, almost there. Any questions about how that works? Everybody's coded this up themselves? Okay, that's good. Okay, I think the transformation is almost complete. Let's go and look at the output. The output is actually being saved here to a directory. And the output is a sequence of images, which is the morph, right? So there it is in more real time. Okay, so that was our initial run, right? What did we just see? We just saw this part. Right, now what's happened in the background is our system has actually cached a lot of the intermediate results and the dependencies between them. And now what I'm going to do is I'm going to open a second morph, and that morph has a slight modification. And so there's the modification. So essentially, I took the original images, I added some text labels, and otherwise the images are identical. The morph lines are the same. Okay. Now I'm going to tell the application, please do the morph again. Okay. So let's see what happens, aside from some little GUI things. Now, it's a little bit faster this time. Or as my son used to say when he was very small, a lot a bit faster. Okay, so that was the morph the second time around, and I think when we measured it experimentally, it was like a 37-fold speed up, right? And it's not really a big surprise why we should be getting such a speed up, right? Why is that? Well, the inputs to the image are changed in a very small way. There's a small change to the inputs, which yield a small change in the outputs, right? And if we're caching things properly, remembering intermediate results, we can reuse big parts of the computation. And we can even do a better job reusing it if they were done in parallel. So here's the very basic idea behind what you saw. The way to parallelize this algorithm is to divide your images into tiles, right? And then if we look at a particular tile in the output, for example, tile 3 here, and we look at the dynamic dependencies, that is, what other tiles does the output tile 3 depend on, it's going to be a function of some other tiles. And because of the morph lines, which were static here, it turns out that this lower quadrant tile is basically dependent on these other 3 tiles in the input image, but not in the tile on the upper left, where the change happened to be, right? So in the case, what you saw here was that the lower quadrant essentially was an output that was unchanged due to the change in the input. But how did we know that? We didn't want to code all that information explicitly. So the challenge is really to come up with a programming model that will allow us to express this parallel computation in a way such as to enable this incremental self-adjusting computation. So again, the idea is we want to leverage parallelism for self-adjusting. Or think of it the other way around. If we have an incremental algorithm, we could also think about how we would leverage parallelism to make it faster. So it works both ways.
Question.
Yeah.
So before you start programming, do you need to think already simultaneously about being able to increment and being able to do parallel those?
Yes, so our thesis is that data decomposition and algorithm decomposition is central actually to both incremental and parallel computation. Now, these days people are more concerned with parallelism because of all of the available parallelism in hardware. So we think if we start with a parallel programming model, then you've identified independent tasks and dependent tasks. You've done a lot of the work already that would be helpful for incremental. So our observation is really that what's good for parallel is also good for incremental, and perhaps you can get incremental with a little extra effort or not much more effort over that. But yes, there's thinking involved. We're not proposing an automatic parallelization or incremental algorithm. So there's, as we'll see in the experimental results, it's a tool that you use, but you do have to think about data decomposition and task decomposition. Mm-hmm.
The program that is computed incrementally, will it be decomposed to be executed in parallel or no?
Right. So in our framework, when you need to reevaluate, if there's sub-parallelism there, we will do the incremental update in parallel as well. But that parallelism has to be in your algorithm. We don't add it for you. No. So the other way to think about it is, where does incremental work well? It works really well when there's tiny changes that propagate to tiny changes in output. If there's not a lot of computation involved in that, parallelism doesn't work so well. On the other hand, if most of your input changes, most of your output will probably change. In that case, incremental doesn't work so well, but then parallelism helps you. So by having sort of a framework that allows both, you're able to adapt to big changes and small changes in the ideal ideal situation. Okay, so let's start first with the incremental part. So what we do is pretty standard here. If we have this loop, how do we think about making it incremental? And so what we do is we essentially we do loop unpeeling. We peel out the compute phase, okay, and we have this record operation, which essentially says, please memorize some things. Please remember this computation for me because I'm going to repeat it over and over again. So it's a very high-level declaration. It's saying this is interesting to me. Please record it and remember it for future use. Then our loop now does the mutation as before, and now when I want to redo the computation, I invoke the repeat command. So essentially, record says, here's a piece of code that's important for me. It's expensive. Please do some smart caching or smart memoization so that I can later repeat it. And this is essentially, these two primitives are essentially the idea behind self-adjusting computation with a bunch of other primitives, special data types and such, and dependence tracking. But the idea is really we should think of these two programs as a semantic specification of what we want out of incremental computation. So we want these two programs to be equivalent when we observe the behavior of the repeat phase. If we think about sequences of compute, mutate, we want essentially equivalent traces. Now, I haven't said anything about parallelism or how we're going to achieve this, or in fact about performance. I mean, we want some good performance, but we think of having this ability to really say, here's a piece of code, and I want to record its effect, and then replay it or repeat it after a mutation. Okay. So now the second part is our parallel programming model. If our compute phase is sequential, then previous work has shown how to do this transformation and make it efficient for certain types of programs. But the question is, how would you do that if you were going to parallelize your compute phase? Remember that compute phase, we assume it's deterministic. If we parallelize it and introduce data races or non-determinism, it's going to be very hard to talk about its repeated behavior and giving predictable results. So we need a parallel programming model that's deterministic. And we chose the one that was created by Sebastian and the others at Microsoft Research presented in OOPSLA 2010. It's called concurrent revisions, and it has primitives called fork and join, but it has a notion of isolation. That is, when you fork a task, that task gets an isolated view of the state. And we'll go into some detail about how that execution model works. So let's just take a look at what a program written with concurrent revisions and record and repeat looks like. And this is sort of a toy example, but it's meant to fit on one slide and give you an idea. So we're doing a parallel summation of the set of integers in an array. Now what we've told, the way we've declared the parallel sum method is with a special type, not just that we have an array of integers, but we have an array of versioned ints. So this is essentially a special data type that we use in concurrent revisions to represent this data that is going to have that's going to have multiple versions as we fork new tasks. Okay, so we're declaring that we have this versioned array and that we want to sum the range of integers, a range of integers. So the body of the code is very classic. If we're below some threshold, then we just do a sequential sum of the members of the array. There's no parallelism. Otherwise, we divide and conquer. We have a special type of version variable called a cumulative int that we initialize to 0, and then we essentially spawn two revisions. One to sum up the bottom half of the array, and another to sum up the top half of the array. We accumulate the results into the sum variable. The sum variable is the special version variable, so it has a unique version for each revision. And when we join these revisions, there's an automatic merge of the sum variable that does what you'd expect it to do. It sort of merges the results. So it's an accumulator, and it accumulates. There's no special code I need. So in concurrent revisions, the main ideas are we have the special versioned type, which lets us track, lets us isolate state. We have the ability to fork off tasks and to merge their results back in. And so in that way, we can do very simple divide and conquer algorithms. So now let's think about the record phase. So the record phase might be something like this. I say, okay, I have this array of 1,000 elements. Please sum it for me. And what is the record phase going to do? Well, essentially, the way we think about the execution is in terms of a revision diagram. So the parallel sum from 0 to 1,000 is our main revision. Think of that as that's our main procedure executing. And at a fork, we're going to fork off some work into a child and continue. Okay, and that revision is a task that's going to sum the elements from 0 to 500, and it's going to spawn another child, and so on. So we have a recursive decomposition that's unfolding. What we're recording is actually the structure of this graph. So this graph itself, this fork join graph, is being memoized. But not only that, we're also remembering essentially the input-output behavior of each branch, of each revision. We're remembering the inputs it read and the output it created. Okay. I'll talk about how we do that later. So the idea is if I come along and mutate the state now, I've recorded a computation and its behavior. And when I say repeat, essentially I can figure out, based on what was mutated, the parts of that graph that are invalid and need to be re-executed, and the parts of the graph that are still valid and whose results can be just queried to do a lookup. So fundamentally, in our invalidation scheme, we're going to figure out that, yes, this code did, in fact, read the array element at index 333, so we're going to have to re-execute. When we get to the parallel sum, to the fork, we're going to see that we had to re-execute the child fork for parallel sum of 0 to 500, because that fork was the one in which we read element 333, and so on. But fundamentally what you see here is that the dotted gray lines represent revisions that did not read that element, whose behavior essentially does not need to be replayed. Okay, so fundamentally we are going to have to do some re-execution of the skeleton, but not all the inner parts of the skeleton, only the part that actually got to the point where we actually read array index 333, which was the sequential sum from 250 to 500. So we're going to recompute that value, but we're going to reuse the value computed here for the output and the value computed here. So this is the fundamental idea at a very high level. We have a fork join structure that creates this graph. We call these graphs revision graphs, but essentially you can think of them as task graphs. And we use the tasks as the level of memoization and re-execution. Okay, so that's a very high level overview of the approach, and I'll take any questions now, because next we're going to do a deep dive more into the semantics and how the thing actually works.
So to benefit the incremental computation, you want to say you want to partition the tasks as fine-grained as possible?
Okay, so the question is, should we partition the tasks as fine-grained as possible for the benefit of incremental computation? So it turns out the answer is no. It might seem like you want to do that, but there's an overhead. Just like in parallelism, there's an overhead for creating tasks. That's the overhead to schedule the tasks and to do the coordination. In incremental algorithm, there's an overhead in this idea of dependence tracking, of tracking the dependencies. So the finer and finer granularity you track, the more you have to track. So there's definitely we find, as with parallel algorithms, there's a granularity at which it doesn't make sense to do it. It might seem like, yes, you want to do it at the finest level, but then for each of the reads and writes, you're introducing overhead of tracking. So we'll come to that in the experimental results. It's a very good question.
But my follow-up, the question was intended for the follow-up question. So you want the programmer to think about the granularity.
You have to think about decomposition. So yes, there you have to think about decomposition for both parallelism and incremental. And what we're saying is that there's no free lunch there. Okay. What we hope is sort of more free is if you've thought about it for parallel, then doing it for incremental is really incremental. It's almost free. Not quite, but pretty close. But yes, I mean, these are hard problems, both parallelism, parallelizing and incrementalizing. All right. Okay, so this is review more of this OOPS Law 10 paper, but I do want you to understand a little bit more than my cursory overview of concurrent revisions. So we think of sort of revisions as a logical unit of work that's forked and joined. And then these version types, we also call them isolation types, as providing providing automatic copying and merging of different versions. Okay, so in our model, we have determinism. We never sort of abort a computation or roll back. The tasks we have can be long running. They can do I/O, and there's full concurrent reading and writing of shared data. So we're after a deterministic parallel programming model, and it has several attributes. Okay, what's new here is really two things. One is the isolation of side effects and deterministic execution. So let's take a look at a traditional task and see how it changes with concurrent revisions. So in a traditional task, maybe I declare a shared variable x, and then I fork a task that's going to, in parallel, set x to 1. And now I have a main thread that's essentially executing in parallel with that child task and is going to, at some point, join later with that task. Now, after we do the join, we certainly hope that x is equal to 1 because x was initially 0 and the child task forked after the assignment of 0 to x. But what we don't know is sort of in the middle when the main task and the child task are running in parallel, what's the value of x, right? It sort of depends, right? It depends on whether the child wrote to x or not. So it could be 0 or it could be 1. Okay. In contrast, in concurrent revisions, we declare x to be a versioned variable, and the revision gets its own logical copy of x. So at the assertion, there's no question about what the value of x is. It's the version in the main task, in the main revision. Okay. The child's effect is not visible on state until after the join. So essentially, we're eliminating non-determinism by isolating state, okay? And this gives us tasks that are essentially atomic in their nature, and it also gives us deterministic results, which all this says. Okay, so let's go through a couple puzzles just to make sure this is clear. So instead of like looking at a program like this in text, we're going to use what we call a revision diagram. And this really corresponds to our intuition that because of the isolated nature of revisions, we think of these tasks that are forked off as branches in like a version control system. So you branch from a known state, you get a copy of that state. And then when you join into it, a branch, you're merging together the values. So let's imagine that these assignments, these updates to x and y are atomic statements for the purpose of this example. And that x and y are initially set to 0. And then essentially we're doing a fork of this child that's going to check if x is 0 and increment y, while the main revision checks if y is 0 and if it is, increments x. So my question to the good audience is, what are the possible final values for x and y?
0, 1, 1, 0. Well, correct values?
Under assumption of sequentially consistent execution, which I, okay, so, the assumption that those assignment statements, those increments are atomic. 0, 1, and 1, 0 for x and y, and 1, 1. Very good. Right, so if we think about it, what if the child runs before the main revision? Well, then it's going to be, then we're going to increment y to 1. Maybe I should write this down. So we can think of these code blocks. This is always confusing. Let's call this one A and this one B. So A can come before B, or B can come before A. Those were the two cases you were considering, right? But there's a third case where let's call this guy A prime and this guy A double prime, right? There's also something where both of them check if the conditions in parallel and they both succeed, and then both x and y get incremented. So we get x equal 1 and y equal 1 in that case. So is that clear? Those are the three possible scenarios. This is what makes reasoning about concurrent execution, even under sequential consistency, really tricky. You know, for that simple little program, you get 3 different results depending on the interleaving. Okay, if somebody comes along and gives you a transactional memory system, then we're in better shape, right? You're a database guy. You always think about transactions, right? So if we think of these things as atomic, that they can't be interleaved, then either you get A before B or B before A, and you get one of these 2 results. But still, it's still non-deterministic, right? Under concurrent revisions, so under concurrent revisions, what happens is y is always 0 in the main, and x is always 0 on the right. So you always get 1, 1. In this case, the child and the main revision are writing to disjoint memory locations, and the merge is just very simple. Okay, so the good thing about getting of isolating and having this notion of these snapshots is that you do away with non-determinism.
So the semantics are still not super intuitive. Right? What I would like to think is that I'm always going to get A followed by B. Completely, it would never happen unless I was running in parallel.
Right.
And I can't just align the forks and get some sort of.
Right. So what you can do as a programmer is control the joins. So let's talk about that. So what happens on the joins, right? That's the interesting part. And the good part is the programmer has control over that. And we also have a default resolution policy that can be overridden. So in concurrent revisions, on a write-write conflict, child always wins, unless you want it different. So in this revision diagram, the main revision updates x in parallel with the child, and the child wins. X is equal to 2 at the end. Sorry. If you want it differently, then you have to override the merge. But it also matters that we track whether you wrote or not. So in this case, even though main writes 1 and child writes a value that was already the same value in the snapshot, well, remember, if child writes the location, child wins. Yeah.
What happens if arbitrary overlap happens between the 2 sides? Then you get something that is a jumble of the 2, right?
So what you're asking is, what if I have x and y, and I update both? Right. Child wins.
No, not always. I mean, you could have XYZ and YZA.
Yeah, so, well, we saw that already, right? So child wins on things which are conflicts. There's no jumble, it's very clear. On anything where there's a conflict, that both sides have a right to a location, child wins, right? So yes, if the main revision wrote a location and the child didn't, then there's no conflict.
I understand that, but from a sort of high-level consistency point of view, it's very disturbing that part of my computation vanished. And
Okay, so it didn't actually vanish. So the good news is there's a default behavior, and what we find is for the applications we've looked at where we've used this so far, games in the browser, that this strategy works pretty well. And as a default, it covers a lot of cases. Essentially, when you have multiple updates going to different partitions, generally the case is you just want them all, and that's like in parallelism too, right? Now, if you have an invariant, and that invariant mentions multiple data items, right, multiple parts of state, you might be worried about, I need to update X and Y together. Then, it's up to you as a programmer to ensure that those updates will be done, right? Because it's certainly, if you had an invariant about mentioning both X and Y, then if X was updated on one side and Y was updated on the other side, then an invariant might not hold at the merge. I think that's what you're finding confusing, right? But in that case, our argument is you have an invariant and a data type that you should be specializing a merge function for.
So if I write x equals to x, does that win?
Where? If you do an update. If you do an update.
If the compiler decides this is pointless and elides it, does it still win?
Well, that would be a bad thing to do, but we can talk about promotion of memory to registers, and compilers already have that problem, right? I mean, you have to be very, very careful.
Part of the reason you have these semantics is to guide the compiler is
Yes.
So the semantics that you described then include the ability to construct an erasure theorem that allows me to erase fork and get behavior that's equivalent to sequential behavior?
Yes, in fact, our model is not sequentially consistent. It's snapshot isolation.
No. The question is, I want to be able to come up with a merge function in which the behavior of the merge function is equivalent to as though I erased all of the forks that I had. So I essentially get safe futures or something like that. And the question is, so I'd like to be able to reason sequentially, right? That's my notion.
But wait. But you have a fork, but you still have joins, but you don't have a fork?
So I'd like to reason sequentially.
Sure.
Right? So what I would like to do is to be able to make an assert that says the behavior of the assert is as though I ran these things, your forked guy and your main guy, in a way that essentially gives behavior, where the behavior is as though I were running sequentially. Because after all, that's sort of the simplest model that the program can envision.
That's not our model. I think that's very hard.
Okay.
I think that program transformation would be very complex.
Yeah.
It would be non-trivial. Because if you just sequentialized and put one after the other, yeah.
Because you've got this because you've got the merges sort of overlapping on disjoint.
That's right, unless you override that. So it's not SC. Yeah. But his point is you could simulate. His point is I think you could still simulate it somehow, maybe. But that simulation would be tough. Okay, let's talk about the full model. In the full model, the actual, and I do have some other. We're doing okay. So in the full model, actually, we have 3 versions to think about at a merge. So really, if you want to define your own merge function, you can do that. And when you do, you get, just like in merging of versions in a source control system, you do a 3-way merge. Okay?
So you say merging in the source control system like that's something everybody intuitively.
Do people know about diff3?
Right.
You don't?
SVN merges, for example, are incredible.
Yeah. No. I'm just doing an analogy. It's just an analogy. So.
You're analogizing to something that's difficult.
Well, hopefully for integers it's a little easier. So the idea is when I fork, I have a state, right? In that state, I can think of that as being my my original value of x, which in this case x equals 0. As I'm progressing, I'm progressing in parallel in 2 branches. One of those branches is the main branch, and at the end of this branch, x is equal to 1. And at the end of this branch, x is equal to 2. And so when we want a custom merge, we can write that merge. And that merge is lambda, which can be a function of 3 states. The state of the variable at the time of the fork, which is a ridge, and the states coming into the join. Okay, so for our cumulative int, which we used in the parallel sum example, the cumulative int adds the values of main and join and subtracts off the value at the fork. Because if this had not been 0, but for example, some n greater than 0, we don't want to double count it by just adding in. Okay. So if you don't like our merges and our defaults, you can, at the merge point for every data type, you get a handle on these 3 values. You can do whatever you want. And you know which is coming from where the fork value is, what's your main revision, and what's your child. So you actually have complete control over the merge, and you also have order. You also have complete control over the join order. So it's definitely simplifying some things. You're getting determinism, but in exchange for that, you've got to think about these merges because we don't have a retry semantics. Execution always continues. Okay.
I understand the computation has 3 states. At the fork point, then all the processes input the same values for the, like for shared variables.
Yes,
Now, in the second stage, then everybody work on their private copy.
that's correct.
Yeah. Then when join, then it's time to commit. Then
Yes.
you want to follow a certain order. There's a priority with whose value.
That's right. So for example, in a game loop, like we parallelized a game and used revisions, you might have a very long-running revision that's doing autosave. So you have your main revision, which is your game loop, and off of that, at some point, you decide, I want to save the state of the game. You just fork a revision that actually is going to save it, and you're going to join much later. Then what you might do next is you might do something to do collision detection, right? And then you might do something to get network updates, and then you might do something else. Now, all these things are going to happen in parallel, but you get to control the order at which the effects join. So, for example, you might do your collision, and join, but then you get your network and you decide, oh, I want the network to take precedence. So before you update your display, you've actually made a choice. You've actually made a choice to join on the collision detection before you do the join on the network update. So you can essentially prioritize, what updates you want to see when you know there are going to be conflicts. So that the join order is essentially like the arbitration order, and you control that as a programmer. Okay, we've got to get to incremental. So that's I think the really important part is that if you're going to think about incremental algorithms on top of a parallel algorithm, you want determinism. Now, you may not agree with our way of getting a determinism, so it would be interesting to say, oh, if you have another parallel programming model, how do you make it incremental? And so we think there are certain parts of the concurrent revision story that would apply, but it should really be deterministic because we have no idea what to do with non-determinism. So our design decisions for making it incremental is that these revisions, these tasks that we fork and join, are actually the units of memoization. So when we decide to make something incremental, we also have this granularity question, like what is it I'm making, what am I caching? Am I caching function calls? Am I caching expressions? Am I going very fine grained? Our decision is to keep it pretty coarse grained. Whatever you decided was good for parallelism, that's our unit of memoization. And if you want to do something else, then that's outside. So we call a summary the result of executing a revision. So when you execute a revision inside a record phase, we want to track all the values that the revision is reading to know what are its inputs. And we also want to look at its final writes. The nice part about concurrent revisions for this is that we are already, through this level of indirection with the version data type, we are already sort of tracking the information because in order to do concurrent revisions without incremental, we need to do efficient copy on write. So when we logically think of making a copy, we actually don't do the copy. We have to track sort of how the data structure is being written to and read from. So one idea is that if you already have a level of indirection you're paying for sort of doing things like making logical copies of state, then you're piggybacking incremental dependence tracking on that is not terribly expensive. So the basic idea is that we are tracking the summaries at the level of revisions. The repeat executes in parallel, just as the record phase did, depending on your fork join structure. And we do dependence-based invalidations of summaries on writes, as I alluded to before. So the way to think about this is we have this revisions graph that I showed you before. And what our summary is basically an isomorphic sort of tree that's recording these summaries. So we're creating an ordered tree of summaries where each summary here corresponds to one of the revisions. And that summary is recording not just the fork join structure, so it's mimicking the skeleton, the synchronization skeleton, but it's also recording the input-output behavior. And so we're keeping this tree around. In the case of the morph application, this tree represented the recursive decomposition of the images into subtiles and the computations on those subtiles to create the output matrix. So as I said, the revision library is already storing for us the effects of executing these revisions. We can track these dependencies and invalidate summaries. And we do the invalidation only at the time of, we invalidate on writes. And at the time of the fork, we can safely determine if a summary is valid. So let's just take a small example here. This might be, for example, the CSS layout algorithm, which we parallelized here. So in the paper, there's more detail on that. We're recording essentially 3 traversals over the tree. And so in terms of our revision diagram, we can see those phases reflected. We can see those phases reflected here. Now, it might be that one of these phases, like the first phase, in one of these leaf revisions, it reads the variable x. Now, if we then we then say we have a dependence on x, so if we see a write to x now, we are going to invalidate any revision that directly reads x and all its parents. So fundamentally, what that means is, as you saw in the parallel sum example, we're on repeat, we're going to re-execute the parent. When we get to a fork, we're going to determine whether we need to re-execute that fork, and we're going to descend to essentially re-execute this this child. But potentially, many of the other revisions do not have to be re-executed. However, the execution of that revision that depended on X, that may write some new locations or existing locations with new values. So the re-execution of that invalidated summary will actually cause other revisions or other summaries to be invalidated. So then as we go to pass 2, we might have to re-execute more. Then perhaps that second invalidated summary, it affects many things, and then we have to re-execute the third phase totally. But there we're going to re-execute in parallel because underlying our computation is parallel. So again, if there's small changes to the input in our dependence-based invalidation scheme identifies it precisely, we get the benefits of incrementality. If the dependence-based invalidation invalidates a lot of things, well, hopefully the parallelization will still help us there. Now, that all sounds great, but this invalidation is really tricky, and that's sort of the core problem that we address in the paper. You're recording this arbitrary computation that may depend on external input, which is invalidated between the compute, the record, and the repeat phases. Furthermore, some later computation may depend on an earlier computation, and both of those may be in the record phases. So you need to deal with the problem of writes disappearing, that is, locations that were previously written are never written now, or you write new locations that you never saw before when writes disappear. And the dependencies between the computations can change. So at the end of an invalidation and a repeat phase, you want your invariant about the revision diagram to be maintained. That is, you want to be able to take another modification and do it all over again. So you also have to update incrementally all the internal bookkeeping that we're keeping. And you have to do it all correctly concurrently. So in the sequential case, doing this invalidation and doing this recomputation is simplified by the fact that you're in in a sequential setting. When you want to preserve the existing parallelism in your application, then you want all of this to happen concurrently. And really getting that right is tricky. And I'm not going to say anything more about that now, but you can look at the paper. So coming back to some questions, what does a person have to think about? And you still have to think in this case, okay? The programmer is going to think about the structure of computation and how to decompose it using fork and join. You have to also decompose your data to think about the data that participates in concurrent accesses and the dependencies, and when there are conflicts, how to merge. And you also have to think about performance, right? Just like in parallelism, you have to think about the granularity at which you want to do things. And there are various optimizations that you can apply for both parallelism and incrementality. It turns out most of the ones you apply for parallelism are good for incremental, but there are also some tweaks for incremental. What our runtime does for you is it's going to do all the dependence tracking. So you just declare, these are my version data types, and all this dependence tracking that goes forward to do invalidation is taken care of for you. All the work of creating these summaries that define what is the I/O behavior of revision, it's done automatically. And underlying, we have a task-based scheduler that's doing the parallel scheduling for you. That's just provided by .NET. So really there's still a bunch to think about, but most of what you're thinking about for parallelism is being leveraged for the incremental computation. So the optimizations that the programmer needs to think about are sort of classic ones. The first that's shared with parallelism is the control over granularity. If revisions are very fine-grained and don't contain enough work, then both parallelism and incremental will suffer. And so here you have to use typical techniques to have the revisions be large enough. If they're too fine level, then there's overhead. So we're not talking about creating millions and millions of revisions. The other aspect is the level of granularity in memory accesses. So for example, if you want to do dependence tracking at the level of every node in a CSS tree or in the DOM, you're paying dependence tracking for every read and write. Instead, maybe you want to do your dependence tracking sort of at subtrees of certain types and have a read or write abstracted to a single a read or write to a set of memory locations abstracted to some representative. So you can in the case of our morph example, we did not have a read or write per pixel. Right? We had our granularity set at the tile, and a read or write into the tile was captured and marked at that point. So there we have special objects in our library. Okay, let's finish up with just a little bit about the evaluation. So what we did was we took existing applications. So these were applications that were not written by us. Most of them had parallelization applied to them already. It wasn't necessarily concurrent revisions, but it was task-based. So we first had to move it over to use concurrent revisions. Baseline is the time that it took on our benchmark for each of the examples for the parallelized version, okay, without doing any of the incremental tracking, okay. So you can see here, and these are measurements on an 8-core machine. So the first thing is to say, okay, what happens when we do parallel record, okay, and so actually, is this true? Did I misspeak? No, I'm sorry. Baseline is without parallelism. That's sequential. Okay. The next is parallelism plus recording the computation, the core computation. So what we can see is we're getting speed up still. We're not getting anywhere near an 8-way speed up. In fact, if we just do the parallelization, most of these examples we're lucky to get around 6. But the point is that the record phase, although it adds additional overhead, we're still getting speed up. Okay, so what I don't have for you here are the numbers for the parallelism, but essentially recording is still faster than the recording is faster than the sequential baseline. So we're not, we're taking advantage of parallelism, but we're not getting the full speed up. What's really remarkable is what happens when we make a modification and do the repeat. So in this case, as you saw with morph, we can get tremendous speed ups by leveraging the work we did in memoizing on an incremental update. So here we're seeing anywhere from a 12 times speed up over the baseline to 37 times for the morph. And then again, if we think about what's the cost after doing a large change, well, the cost after doing a large change is essentially the same as doing a parallel record. It's like doing the whole computation again with no memoization. Okay. The other question we often get asked is, what part does parallelism play? So what if we did record without any parallel execution? So here you see the answer to that. So this is the baseline execution sequential, which is 1 here. If we don't use parallelism, then definitely record costs us. And it costs us about 31% on average. So parallelism is definitely helpful during record to take our overheads down, right? So we really think of doing parallelism and incremental together. But then, are we getting a big advantage from parallelism during incremental change? And that's the second, that's the repeat phase here. You can see on the ray tracer, we actually did get a nice little speed up, but on most of the cases where we have a very small change to the input, the incremental algorithm is so efficient that we don't have a lot of computation to speed up. Again, without parallelism, we take a significant overhead for the record phase, so you definitely want to think about incremental and parallel together. We think they do work pretty well together. So just to sum up, the contributions of our work, I think the first is sort of more philosophical. It sort of says that what's good for parallelism is also good for incremental. And we think if you've done the thought and the hard work to decompose your data and your computation into task-based parallelism, that you can get the benefits of incremental without a lot more work. Our particular take on how to do it was this model for deterministic parallelism called concurrent revisions, but we believe that other approaches could be used here. The essential idea is that we use these revisions or tasks as both the unit of parallelization and the unit of memoization. And then we've done the implementation. It's all library based. So everything you saw, we were taking C# programs that were essentially using task parallelism. We converted them with very little code over to concurrent revisions, and then added a few more lines for the incremental. So these were existing applications not written by us, and I think the library approach really helped us out here. So I think that's it. Thank you.
We have a few minutes for questions, and then there will be colleagues outside.
Great. Yes?
How much effort was adding the revision stuff?
So the main effort is you have to identify sort of the state that you want to be isolated. And so that's sort of the toughest part, because you've got to look at this existing application and you've got to sort of say, okay, here are the tasks, and what is the state that they're reading and writing, and what do I have to wrap in these version types. The good part is we actually have an inference engine that comes with the tool. So what you do is, once you've identified the types, the story is not over. You also have to use getters and setters rather than direct access. So, because we're adding a level of indirection in order to be able to do all this dependence tracking. So we have a type inference tool that once you put declarations on your variables you want to be versioned, then it basically goes through the code and rewrites it for you. So we have a little refactoring tool that helps you out. But you have to sort of decide, and if you get it wrong, bad things happen. Because fundamentally, if you've got like a variable that's not versioned but should have been, you're going to have a race. So we also have a race detector, right? So this is, so look, we're writing in C# and our revisions are a library. So if you had like something like X10 or your favorite statically typed language that really prevented races or something, you'd be in a much better shape. So there's still work to do, but fundamentally, we were starting with programs where people had already done the data and task decomposition. So it would be even harder. I guess that was the good part for us. But if we were just starting with sequential code, then you would have the even bigger question of, wow, how do I take the sequential algorithm and redo it for parallelism? Yeah.
What's so you're doing record by you rewrote your program in concurrent revision, then you're doing all this memoization and stuff like that.
Right.
What's the overhead of just the recording aspect of that? So if you just use concurrent revisions to parallelize the programs without does doing the recording add extra overhead, or is it more or less just a cost issue?
Well, the graph I showed was about the overhead of record compared to just sequential, right? Which is about 30%. So that's the best way I know how to tell you about the overhead of the dependence tracking, is just to measure it without the parallelism, right? So basically you're intercepting these reads and writes. So if you're reading data over and over again, reading it a lot, you potentially pay quite a bit. You want your amount of computation for your reads to be big, right? So for example, with like the tiling, right? It's nice, that the tiles be big enough, right? And also that the other thing with the tile was that I don't want to track every pixel, right? So there, we have a tile abstraction that adds another level of indirection, and we track the reads and writes on tiles. So this is very in line with sort of Pingali and everybody's view on parallelism. You want these higher level abstract views of your data to think about parallelism, and I think also both incremental. If you're really trying to do everything very fine grained, your overheads are going to be enormous. Like, you're just going to slow down, for tracing every memory location, it's just incredibly expensive. So you have to be very careful about that.
Let's thank the speaker. And there's
Okay.
somebody else.
Thank you.